Hello again. Today I'm back in school, which is why it might be a bit noisier. And I'm going to do a video looking at the two binomial questions that have come up in the two practice papers we've done. Binomial is on the revision list, so it's worth doing. However, some of you might say, right, I've done those two, I'm sorted with that, you may choose to go and do something else instead. That's fine. This video will just look at revising binomial. And that's because I was going to do transformation of graphs, looking at trig graphs in particular, but I think that's best done when we're back in school, and I'm fairly confident we'll be back in on Monday. So we'll do that Monday, Tuesday and Wednesday when I'm hopefully back in front of you. Anyway, if we're asked to expand this, the good news is we don't need to do it the long way. We don't need to grid it out. You just need to remember that we start with this, which is predictable. We know that this is predictable. The expansion of this, if we did do it the long way, would have a term with a to the power of 4, a term with a cubed times b, a term with a squared, b squared, a term with just a and b cubed, and a term with b to the power of 4. And each of those terms would have a coefficient. And we can work out those coefficients from Pascal's triangle. We need 5 of them, so it's the row of Pascal's triangle that has 5 coefficients, or we can use the NCR button on our calculator. So this first coefficient is 4, which comes from the power, C, 0, which comes from the power of b. There's no b there, so that's 4C0. We've then got 4C1, and 4C2, 4C3, 4C4. So can you remember how to get the NCR button on your calculator? So we're in normal mode. It comes under option, and we need to go to the second page of options and choose probability. And there it is. Bit hard to find, but once it's there, it's there. So I'm going to do 4C0, which you'll remember, I'm sure, is 1. And in fact, the first and last coefficients are always 1. I'm just going to turn the brightness down. Hang on a moment. There we go. And 4C1 will be 4. Let's change back to black. And that's always 4. Sorry, still got brightness issues. To there. From then on, though, I'm a bit shaky, so 4C2 is 6, and of course it's symmetrical, so now I'm pretty sure I know what's going to happen next. 4C3, yeah, that's 4, and 4C4 will be 1 again. So there we go. And those terms are added, so it's that, plus that, plus that, plus that. And then all I need to do, if I want to do 3 minus x, is I then need to just make a equal to 3, and this is where I need to be a little bit careful, b is equal to minus x. I'm going to put that in brackets. So go on, if you're doing this with me, do that substitution for me now to get the expansion of 3 minus x to the power of 4. I'm going to pause and come back in a minute and do it. So I've done my substitution, been really careful about the minus x, made sure I've got that in brackets. Let's simplify it out. You don't have to do it down like this, it's just that's the way I like to set it out. But now I'm going to write it out in a line. So 3 to the power of 4 is 81. And then I've got 4 times 27, which is 108. And that's multiplied by minus x. So that's actually minus 108x. I've got 6 times 9, which is 54. Minus x times minus x is plus x squared. So that's plus 54x squared. 4 times 3 is 12. Minus x cubed is minus x cubed. So that's minus 12x cubed. And minus x to the power of 4 will be plus x to the power of 4. So that is my final answer. Let's have a look at the the two questions from the past papers then. Okay, so I'm going to do the question from paper 2 first, which is the easier of the two. This expansion, I'm going to start by doing a plus b to the power of 7. I'd already messed it up by thinking I was doing a plus b to the power of 4. This expansion would have 8 terms, but the good news is we're only asked for the first 4 terms. So a plus b to the power of 7, that would be an a to the power of 7 term, an a to the power of 6 term, an a to the power of 5 term, and an a to the power of 4 term. It would obviously carry on. We'd have a b squared, and a b cubed. And then we'd have our coefficients. I know the first coefficient is always 1. The second coefficient is always the same as the power. So this is going to be 7c2. So 7c2 is 21. And this is going to be 7c3. Remember, the second number is always the same as the power of b. So 7c3, which is 35. Then going to now replace a with 3 and b with x over 2. So why don't you pause the video at that point and have a go if you haven't already done so. Okay, so I've plugged in the numbers, so I had 7 times 3 to the power of 6 times x over 2, 21 times 3 to the 5 times x over 2 squared, which is x squared over 4, and 35 times 3 to the power of 4 times x over 2 cubed, which is x cubed over 8, and I get this. And with these terms here, you know, it doesn't matter whether you write it as 5103 over 2x or 5103x over 2, same thing, okay? So that was the answer to that one. Let's have a look at the second question, which was on the first practice paper. Okay, so here's that question. It was question 10 on the first paper. So let's start with here. We're only asked for 3 terms. So I've started off a plus b to the power of 8, and I've done my a plus b expansion, and I'm now about to replace a with 3 and b, being really careful, with minus x over 5. Okay, so I invite you to pause and have a go at that. Okay, so some pretty horrible numbers here. So I've got 8 times a to the power of 7 times b, which gives me that. And then I've got 28 times a to the power of 6 times b squared. So this is going to be plus x squared over 25. So that's why we get that. Okay, so let's look on to here. So we've got to now take our answer to that and multiply it by ax plus b, and we're told that that contains those terms there. So I am going to take my answer here and multiply it by ax plus b in a grid, and then we'll have a look and see how we can use that to work out the values of a and b. Pause and have a go. Okay, so multiplying it out gives me all these terms. I haven't bothered peanutting it just yet because I don't need to do the full thing. So I know the full expansion contains that constant term, no algebra. Well, this is the only constant term I've got. So that tells me that 6561b has to equal 32,805. So that means that b is 32,805 divided by 6561. B is 5. It's nice and easy. And the only place where I've got x terms are here. So altogether, I've got that many x's, and that's got to equal that many x's. So that tells me that 6561a, which is the number of x's here, minus 17496b over 5, that's the number of x's there, has to equal minus 1474. Now, I already know what b is. B is 5, so that's good news here, isn't it? Because if I multiply that by 5 but then divide it by 5, I'm just left with 17496. So that then becomes running out of space, sorry. There we go, that's better. And it's some nice easy algebra then, isn't it? I'm going to add that to both sides, so I've got minus 437, sorry, I've got minus 4374, and I'm going to add 17496, so that gives me, and I'm going to then divide that, so I'm running out of space again, I'm going to divide that by 6561, and A is 2. And that's the end of that question. Good stuff. Right, now in the absence of any emails asking for solutions to questions on that second paper, I'm going to just tag on one, which is the sort of the proofy question. So I'll do that one now, but if at any point I'm doing this on Thursday, if at any point today I get some requests, I'll just do a separate video. So stand by, I'm going to go through the proofy question from that second paper. So here we are then with this question 9 from the second paper. And it's a funny question because it doesn't sort of fall into any of those nice proof categories. It's a bit of a common sense one. So rational numbers are numbers that can be written as fractions. They're pretty much any number. Rational numbers will always, when written as a decimal, either be integers, whole numbers, or they'll be terminating decimals, so decimals that finish, 0.125, or recurring decimals, so decimals that repeat with a pattern. Irrational numbers are numbers that can't be written as fractions, and if you write them as decimals, they go on forever in an unpredictable way, and the two most obvious examples are pi and e, but square roots of integers are mostly irrational. So I know what the square root of 4 is, that's 2, so that is a rational number, but the square root of 5 and lots of other square roots, I don't know that, and if I do it on my calculator and STD it, I don't get a recurring decimal, it's an irrational number. As a decimal it would go on forever in an unpredictable way. Right. So we have to find two false statements. I think one is easy to spot and the other is slightly harder to spot. The sum of any two rational numbers is rational. That is correct. So if you take two numbers that can be written as a fraction and add them together, you will get another number that can be written as a fraction. And similarly for C, the product of two rational numbers is irrational. Is rational. You can't make an irrational number by multiplying two normal numbers together. Think of normal when you think of rational numbers. Now, the product of any two irrational numbers is irrational. So let's think about the square root of 5. So can I multiply the square root of 5 by anything and always get another irrational number? I mean, for example, if I multiply it by the square root of 3, which is another irrational number, that gives me the square root of 15, which is another irrational number. So that tends to suggest this is true. But that's not always true, is it? Because if I take the square root of 5 and multiply it by itself, another irrational number, I get 5, which is a rational number. So statement D is not true. This is not true always. Sometimes it's true, but it is not always true. So statement D is one of my false, and we have to provide a counterexample. So my counterexample for statement D is that the square root of 5 times itself is 5. So that's the counterexample. So I haven't talked about B, so B must be the other one that's false. The sum of two irrational numbers is irrational. So the square root of 3 plus the square root of 5, well, you can't simplify it, and it is still irrational. And at first glimpse, it's easy to think that maybe this is true, but it's not true, and it's not true for a very subtle reason. 1 plus the square root of 2 is an irrational number. Okay? So 1 plus the square root of 2 is an irrational number, as is minus the square root of 2. That is another irrational number. If I add these two irrational numbers together, I just get 1, which is a rational number. So although it seems that this has to be true, these rather nasty sort of special case examples show that it doesn't always have to be true. And so I've identified the false statement and I've given you a counter example. And you could come up with any one of a number of similar examples to that. So question 9, bit of a nasty proof question. It doesn't fall into one of those categories, apart from, I suppose, it's proof by counterexample. But there we go, that's that. Right, so I'll leave Friday's video here, but I will, at any point over the next couple of days, happily knock up a quick video on any of the other questions in this paper that people ask for. And if not, I'll assume that the mark scheme and your own work is enough. Please keep in touch. Take care.